Thanks. Okay, so let me just start with a quick recap of a little bit of what we saw last time, and then we get going. So we have this Hilbert space of L spin 1/2. And on this, we have two operators that we quite like, or actually maybe three, but okay, so one is the spin Z operator, which will have only Z at all different sides. This was my notation, remember, for sides modulo L. In this case, it doesn't matter much. Then we have the translation operator, G, which shifted by one side. And then we have the Hamiltonian, which I denoted by H subscript delta, which is minus the sum of L in integers modulo big L, the length. And then there are these local Hamiltonians, which I call H, L, L plus 1. In this case, it's really important that these integers are modulo L. And these little h's, H, L, L plus 1, was given by sigma plus at L, sigma minus at L plus 1, plus its Hermitian conjugates for the hopping terms. And then there was the potential part, which is delta over 2, sigma z at L, sigma z at L plus 1, minus the identity just to set the up vector to energy 0. And I will denote the eigenvalues of these things by, well, this by L over 2 minus m. So m counts the number of down spins. Translation operator, well, its eigenvalue is actually e to the I p total, where this p total is the total momentum, which by periodicity is 2 pi over the length times an integer. And for the Hamiltonian, I will write E delta for its energy. So this was the setup. And so what we want to do is the coordinate beta ansatz. So we want to actually find the eigenvectors and eigenvalues of this Hamiltonian. So this was 3, which is the topic of most of today, which is the coordinate beta ansatz. That's the way in which we will achieve this, which normally too long, so we abbreviate it to CBA. And this is, if you wish, this is old school integrability. Quantum integrability. So the idea, as I finished last time, the idea is that the coordinate beta ansatz gives a physically meaningful parameterization of the would-be eigenvectors of the Hamiltonian, and as we will see, they are really eigenvectors, provided that the parameters that appear in these eigenvectors obey so-called beta ansatz equations. So that's the goal of most of today, to see that. So let's start with by some preliminaries. So we want to look at this equation H delta on vector psi is E delta psi. And we can do this at a fixed value of this m, which was the number of spin downs. So remember that we have this coordinate basis. So let me recall notation. So I denote by the vector L with a double kind of wrangle on the following thing. So in more detail, this means L1 up to Lm, which means spins flipped at sides L1 up to Lm to the vector with down spins at those sides. And then let's write properly. So here we have the range L1 less than Lm less than big L. So then it forms a basis for this vector with m down spins. It will be convenient to use the following shorthand. So let me define the same L, but now plus or minus 1, just to mean that we shift all the down spins by plus or minus 1. So 1 to the left or 1 to the right. But of course, it's really to make sure that this thing here, this expression really sits in the same range, we have to kind of be very careful. We should do this modulo L, because we had the periodic boundary conditions that sigma alpha L plus 1 was to be identified with sigma alpha 1. And I guess I should maybe also write that is if you shift 1 too much to the right, whereas sigma alpha 0, which you might also encounter, is the same as sigma alpha L. Right, this was the periodic boundary conditions. So a priori, the components of this vector psi, so the wave function, is only defined for such values of these L's. But there will be inconvenience to extend it a little bit. So we will, and then we have to be a bit careful and so on. So this is the first little bit of bookkeeping, really. So the periodicity, more generally, so here, to make this more precise, let's do the following. Let's say that we identify the vector L1 up to Lm in the coordinate basis with the vector. So we say that this is the same. Okay, important. So we identify this with the vector where the downspins are instead at L2 up to Lm and then L1 plus L. So what I want to just allow is I want to, rather than really restricting myself to this strip from 1 to L, I'm actually happy that we now extend it to any values of L1 less than Lm ordered, with the condition that Lm minus L1 should be less than L. Okay, so if we think of this chain, we have this model defined on the chain. Side 1, 2, and so on, little l, to eventually big L. And of course, this is really periodic, but for the bookkeeping, we kind of have to cut it open somewhere. And I'm happy to cut it open anywhere, and I can kind of even, I don't mind if you kind of count kind of with numbers that are not in the range 1 to L, just as long as we make sure that we cut it open somewhere. This is a good notation for the basis, provided we make this identification. So then, the wave function, psi of L, which is the projection onto this coordinate basis vector of the vector psi, must be periodic. So it must obey periodic boundary conditions, which comes from here, right? So we want psi of L1 up to Lm to be equal to psi of L2 dot 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 Lm L1 plus L. So this, now we have extended the wave function to kind of any strip of length L in Z, really, in the integers. And because of the eigenvalue equation, so I'm just going to write down the answer. Okay, let's say that you can read this first. So it must obey this and the eigenvalue equation, which now becomes a difference equation. Which is the following. It's the sum over all little m from 1 up to the big M, so over all the possible downspins. And for each of these downspins, we're going to make a sum from, let's say, over k in a range which I will specify in a moment. So I just write the sum with a prime for now. Then we have psi of this L, but we're going to replace Lm. So the mth magnon we're going to send to k. So then we already understand. So what this sum should be is it's the sum over all k, which are either in L shifted 1 to the left, or L shifted 1 to the right. But they're not allowed to go to the same place that was already occupied. Right? So I look at all the free places to the left and all free places to the right, and that's where you can hop because of these hopping parts of the Hamiltonian. So any one of the down spins can hop one to the left or one to the right. That's this part. And then on the other side, we're going to get, I think if I get it correctly, minus E delta plus twice m, the number of down spins, minus NL, which I'll denote in a moment, it's a number, times delta. And then here we just get psi of L. And this NL here, this is just the number of adjacent downspins. So in other words, it's the number of overlaps between L and L plus 1. Right? So you look at all the sides and you shift all the sides to the right by 1. And then if you had some overlap there, that means that two downspins were adjacent. So this is just the number of adjacent downspins. So the number of down. Okay, so this is not hard to see. I hope it makes sense. You either hop in one direction or you hop in the other direction, which is accounted for by the left-hand side. And then there's this potential thing which gives you a value of delta if for each downspin except when you were aligned like that. And there's a minus sign here, which is I think the reason for this E delta there. The minus sign in front of the E delta there. So this is the equation that we want to solve, together with this periodicity.
Sorry, I don't understand your notation. Why do you, in the definition, K belongs to L minus 1? So that is the set where I shift.
Right. So this is hopping to the left.
Yeah, the other is
hopping to the right. Yeah, and then I'm not allowed to hop onto a site which was already occupied. So if two downspins were sitting next to each other here, then I'm not allowed to go to that side. So that's why I make sure that I subtract them. Right? So it's just hopping to a free side adjacent. So really this part is mostly, it's just bookkeeping, but you know, different people write different, like you do use different notation. Mine is maybe slightly formal, but I think it's nice because it's very kind of explicit. Other people instead write kind of lots of words, prefer the formulas. So there's the, oh, it's a bit annoying. Do we have it, or should I just repeat it?
It's impossible to do it.
Equation that we want to, I think this one is sort of okay, but this sum. So K is in either hopping to the left or hopping to the right, but not if it was already occupied. Okay, so as a little exercise, so I'm going to just tell you what the answer is, and the exercise is to check this. Let's do this if m was just 1, so just a single downspin. So in this case, let me just write down what this equation becomes. You just get psi of L minus 1, or let's say L plus 1 first, then minus 2 delta psi of L, which I moved to the left now, plus psi of L minus 1 is equal to minus P of delta psi of L. This is the difference equation. So we already knew from before, by translational invariance, we knew that psi of L should be a plane wave, right? We just Fourier transformed the coordinate basis vector with a single downspin, so we got the plane wave as a wave function. And then you can just plug this in there, and what you will find is that the energy of this state is, so actually I will denote this by epsilon delta P, which by definition is just the E of delta at m is 1. But now I think of it as a function of p, and it is twice delta minus cosine of p. So this is the dispersion relation.
Sorry, where did that come from, this equation?
This one?
No, the difference equation. You have the...
Right, so this comes from, so projecting, excuse me, just projecting the eigenvalue equation onto the coordinate basis. So you just like here, I projected onto the coordinate basis to get the wave function.
Yes.
Now I project this whole equation on the coordinate basis.
Yes, but I get, why do you get a difference equation, just one term? I mean, if I project...
Because there's sum here over m, so any single one of the downspins will be moved to the left or to the right, which is precisely what all these hopping terms do. Right? Remember that my Hamiltonian, so what it can do on a vector with some downspins is, well, if spins are aligned, then this is 0. If they're misaligned, then you count it. That's this part.
Okay, okay.
And then you either hop any single spin, one to the left or one to the right, provided it's unoccupied, which is the left-hand side.
Okay.
Right? So this is really just apply this to the eigenvalue equation above. Then we have explained, so for a single downspin, the difference equation becomes very simple. We plug in our plane wave and we read out the energy. So nice and easy. So there's some sort of interpretation part here. So this here is the potential energy. And this here is the kinetic energy. If you think which part came from the hopping and which part came from the potential in the Hamiltonian. And this is the dispersion relation, so it tells you what the energy looks like as a function of the momentum. And then, since it's an exercise, I can also let you think a little bit. How do you see the isotropy at delta is 1? So remember, delta is 1 was a special point. We will see it come back here. Maybe a little remark. If delta is 1, then the left-hand side here is actually a discretized Laplacian. It's a second derivative, discretized. You move one up to the right, well, usually you see it. You expand the second derivative and you do a discrete version, and this is it here. So it kind of makes sense that plane waves would appear there because it's just a free, discretized free thing, and discretized, of course, because we're on the lattice. But now this delta kind of modifies it a little bit, and actually I don't really know if there's a kind of a nice geometric interpretation of this as maybe a Laplacian on some sort of slightly maybe deformed kind of graph, or I don't really know. So, but anyway, the plane waves still work. I could also say that this delta, I mean, I can always write the 1 here and move the delta parts there, kind of modify the energy. But it would be nice if you can just interpret the left-hand side geometrically. So if anybody knows, I'd be happy to hear. So this really now explicitly diagonalizes the L by L block of the Hamiltonian that we had. So remember, we wanted to do it m by m, and m was 0, it's very easy. We had a single vector. Then for m is 1, we had L different vectors. We knew that they were eigenvectors because they had different momenta, so they were orthogonal. But now we finally know it's eigenvalue as well. So now the goal is to go on. Maybe another little exercise, which is kind of useful to really do it, is to show that the eigenvalue equation really gives this difference equation. So check that the difference equation follows from this eigenvalue equation H psi is E psi. If you don't really see how it works, just do it. All right. So far, easy. Now, the important kind of test case is 2 downspins. Now things will be getting a little bit more complicated. So in this case, the difference equation, let's write it out explicitly again. There's 2 cases. One is the case where this NL is equal to 0. That means that these 2 downspins are well separated. They're not sitting adjacent, right? So let's say this is a well separated downspin. So in this case, Okay, I'm gonna cover the difference equation because I'm going to write it now anyway. Looks as follows. You get psi L1 1, comma L2. This is a little bit long, but it's useful to explicitly write it out. So then we get psi of L1, comma L2 plus 1. And then we get plus psi L1 minus 1, comma L2, plus psi L1, L2 minus 1. And then, of course, we get this 4 delta times the case where nothing changed. And on the right-hand side, we get our minus E delta psi L plus, like this. All right? And then the other case is when the two downspins are sitting next to each other. So we have at most one adjacent pair. Well, let me assume that L is at least 3, so that otherwise we would have to count them twice. In this case, so what happens here is that L1 plus 1 is equal to L2. They're adjacent. Down, down. So in this case, the difference equation looks similar, but a little bit simpler, because they're just not allowed to hop on top of each other, right? Let me again write it explicitly. We get psi of L1 minus 1. This is still allowed, L2. Then psi of L1, comma L2 plus 1. That type of hopping is also allowed. And then we get minus 2 delta, taking into account that this number of adjacent pairs has changed. Psi of L1, L2 is minus E of delta psi L1, L2. So of course we notice that these two equations look very similar. So what you would like to do is we would like to simplify. So could we simplify equation B using, or equation A, let's say, or the other way around. But let's do it like this. Well, not really, because the wave function was only defined when the coordinate basis was defined, and it requires the downspins to be different, of course.
Sorry about that. Can you tell me what is ends up for now?
Right. So it's just the number of adjacent downspins. So they're either, these two downspins are either not sitting next to each other or they are sitting next to each other. And the difference equation is wave functions. So strictly speaking, this is not allowed. So let's assume that we may nonetheless. So let's make an assumption that we can formally, I'll tell you why formally in a moment, extend our wave function psi to now include, well, in general, L1, it used to have to be less than ... Lm. But now we're going to say, let's assume that we can also have these equal. Of course, we still want our restriction that Lm minus L1 is less than the length of the chain to make sure that we cut open the chain anywhere, but we end up with a single strip of length at most L, or of length L. So let's say we may. The reason why this is formally is that this, so note such psi L does not occur in the vector, because the corresponding coordinate basis vector is 0. We have to kind of flip it down, spin twice at the same side, and Pauli minus squares 0. So the corresponding coordinate basis vector is 0. So we don't really extend the coordinate basis, but we just formally extend the domain of the wave function. So if we are allowed to do this, then let's say that we're able to solve one of these equations for the more general wave function. So if so, it suffices to solve the following equations. So firstly, let me write, so I have equation A and B. So now let me define equation B prime, by which I will mean, I hope this is okay, equation A, which I now assume that I can solve for adjacent pairs. So N1 is, L1 is L, and L2 is L plus 1. So this was the case for which it was not valid, but now we assume that we can do it. And then I can subtract the previous equation B, and what I will get is the following equation: psi of L comma L plus psi L plus 1 L plus 1, so two of these non-physical terms, minus 2 delta psi of L1 comma L, L comma L plus 1. And this should just be 0. I'll interpret it in a moment. Let's first write down all the other equations. So what we could take, well, we could take either of these two equations. So since we already modified kind of B, we could take A, but let's take more simply. We will just take B. But now, extended to all L1, L2. Possibly coincident and so on, but first just with this restriction. And then finally we have our periodicity, which I guess I can call maybe C. Let me just repeat it. So it was the case that L1, L2, this wave function should be the same as psi of L2, comma L1 plus the length change. So we have these three conditions that we're supposed to solve, and the interpretation of these equations is as follows. So this one is kind of our wave equation. This is the middle one. This is the one that we really want to solve. But if we solve it, we're solving it for a wave function whose domain has been extended a little bit beyond where we started with. So we have to make sure that among all the possible solutions to this extended wave equation, we cut down to those wave functions that are actually compatible with our assumptions and all the other equations that we have. So what these two equations do is they kind of cut down all possible solutions to our wave equation to those that are really kind of physically good. And this one here, we can sort of interpret as kind of like a, I don't know, let's call it a bounce equation. Because it's sort of, we obtained it by kind of moving two spins on top of each other. So this equation kind of says that they should kind of bounce off each other and they shouldn't really be on top of each other. And then finally, of course, this one here, it is interpreted to be periodic boundary conditions. So this B prime and C, they cut out kind of all the wrong possible solutions to B. That's the idea. All right. Does it make sense so far?
So when you said A or simply B, what does that mean?
Oh, I mean, we can take either of these two equations, and well, I mean, it really doesn't matter. So I can just say, I can just erase it.
Okay, sure. Because the B practice.
Right. So I kind of want to think of the first equation as what happens when two downspins move on top of each other. So I should take kind of B, which is when they were adjacent to each other, and then I'm going to extend it a little bit so that I really move them on top of each other. So then I have a variant of B. So then you would think, okay, maybe I should really take A. But of course, A is more complicated, and we can kind of simplify it now with our extended B anyway, and it's also extended. So instead, I might as well just say good old B, but now extended to also include the non-adjacent spins. So all of these, including non-adjacent.
Sure. I'm okay with the is that claim that B also holds even when L1 is not equal to L2 minus 1?
This is the assumption. So we're going to see that it's going to work. So so the statement, and maybe we can think about it a bit more, but if we can solve these three things, then we have solved then we've solved everything that we wanted, taking into account all the extensions and blah, 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 blah. Of course, we have to check that the wave function that we end up is allowed to have this extension, but this is usually just a formality. It works. So this is kind of this is a sufficient test conditions. It's of course stronger than the original problem because I made a lot of extra assumptions. So I'm looking in some sense for a more special wave function. But at least it has kind of reasonable interpretation. So All right, so let's now check how we're doing. So for equation B, what we're going to note is, well, we kind of recognize equation B looks a little bit similar to what we had here for m is 1. Actually, what I want to say, rather, actually, well, okay, maybe I should not have erased this. Let's just say either A or B. Or B. But I think what I now want to look at rather is equation A. Because equation A has the nice feature that this equation looks very similar to what we had here. One of the two spins kind of moves, and the other one sits still. It's just a spectator, or the other way around. So what we note is that equation A, it just looks like what we had for m is 1, where I take L1 is equal to L. And then I have m is 1, where I take L equal to L2, right? And the other one is just a spectator, the other variable. And according from m is 1, okay, so from our m is 1 case, we know that this should be, well, on the one hand, it should be E delta. Okay, sorry. Let me say whatever you want to say. So we look at this equation here. We know that we have kind of parts just like look like this here, and parts just looks like that there, but now for the other variable. Okay, let me write down what I wanted to say, and then I can see I'm just missing a logical step in my mind now. So we have this part here. So equation A, it looks like this with a spectator L2, and this is with a spectator L1. Okay, it's slightly, but this is really how I can interpret equation A. And so what I want to say, where I want to get to, is that this is really just separation of variables. Right? So here we have a difference equation, and we kind of do it for the first variables or for the second variable. So we have a kind of a separation of variables, but now for difference equations. And what it means, and you can just check the conclusion, but is that if you take the wave function psi to be a product, then it will solve this. So take the product of what we found for m is 1 with two different variables. So let me denote this by e to the I p dot l, where I form a vector with two parameters, p1 and p2. So this solves A with energy E delta is equal to the epsilon of P1 and the epsilon delta of P2. Right? Sorry, I was getting a bit confused myself, but I hope it makes sense. What you see is that this equation here, it looks exactly like what we had here, and it kind of, you can really interpret it as either something for the first variable or something for the second variable. So just like in differential equations, it's like a separation of variable, and the product wave function will solve it. And well, let's add a separate parameter for each of these two things. So this here, of course, is still a plane wave. Okay. I think I'm allowed to erase this now, because I've already written stronger definitions. Let me just repeat I want to maybe keep this up here for a while, that is epsilon b twice delta minus cosine. That was our dispersion relation. Okay, so this wave equation is actually very simple. It's just a sum of two one-particle wave equations. But we now have to check all the other conditions. So this cannot really be right, of course, because plane wave would mean that the particles are free, and kind of physically we know that they interact, they feel each other. So this can't be the correct solution. And so what we see is that this equation, this kind of bound condition B prime, it only solves by, so think of it as you get an equation between exponentials, and you have to satisfy for all possible values of L1 and L2 in our extended domain. So the only solution is the trivial solution where both of these p's are now equal to 0. So this is not good. So we need to account for the interactions. And this is what the beta ansatz does for us. So now we finally are actually going to use the beta ansatz. So far it was just bookkeeping and trying to maybe extend a bit to kind of make the slightly stronger version of our problem, which helps us to simplify the equations involved. And the beta ansatz will help us to actually solve it. So we have our parameters p, which is p1, p2. These are our parameters. And then let me denote psi with a subscript p for the beta ansatz, L1, L2. And we're going to just take a linear combination of e, leave a little bit of space here, so take a note, e to the I p dot L. And then another coefficient, again, leave a little bit of space, e to the I p, let's say p prime dot L, where by p prime, I just mean the p swaps, so p2, p1. Okay, so physically this is quite reasonable. What we're doing is we take our free plane wave, but we're kind of saying, okay, these particles, they might have actually scattered, which is precisely what happened here. So the two downspins, well, the two downspins with their parameters p, they've exchanged positions here. So we're going to just take and note, by the way, that this is also a plane wave, and it still solves this here, right? So it's a kind of a, we found some solution, so let's just look at some linear combination of all possible things of the form that we just found and see if it works. And now these coefficients, if it's going to work, they will somehow account for the interaction when these two downspins are sitting adjacent. And so note that if we would do this, then our assumption is fine. I mean, this wave function doesn't have any poles or whatever at equal values of L1 and L2. So assumption is okay. Normally, this is kind of just a formality, and you don't really check this assumption. But I hope that in the last lecture, I will be able to say a bit about some other more complicated spin chain, which is called the Inozemtsev spin chain. And there, this assumption actually fails, and you have to do something completely different. So actually, this is important to check that this assumption works. So then, our equation B, or actually I called it, I'd rather check A, is still fine, because we just took two solutions of the form that we found there. And then this bound condition B prime. Well, what you find from this is that the ratio of these coefficients A and A prime, it is the following ratio. So it's minus, and then 1 minus 2 delta E I P1 plus E I P1 plus P2 divided by the same, but with P1 and P2 exchanged. So 1 minus 2 delta E to the I P2 plus exponent E to the I P1 plus P2. So note that these coefficients, they depend on the parameters P. So this is why I wanted to leave a little bit of space. You might want to indicate that they actually depend on the parameters P, but not on the positions of the downspin. Okay, so it is really a valid linear combination of those plane waves. And this ratio here is often called, well, denoted by maybe S subscript delta of P1, P2. And as I will try to maybe show more carefully why this is true in a moment, this can be interpreted as the two-body or two-magnon scattering matrix, S matrix. This is what people call. So they call this the S matrix. But notice that in this case, our particles are just scalars, so it's a one-by-one matrix. So it's kind of a, in this sense, it's a kind of a stupid name. It's just a scalar function. But okay, you can kind of interpret it as this ratio tells us how that's an incoming wave and the scattered wave for the downspins swap their momenta, how they scatter. Then I still need to check this periodic boundary conditions. And if you do this, what you will find is the following equations. E to the IP1 times the length is equal to this S matrix S delta of P1, P2. And E to the IP2 L is equal to the S matrix of P1, P2 inverse, which by the way is just this S matrix with P1 and P2 swap. So these equations are known as the beta ansatz equations, often abbreviated to BAE. And note that together they imply that E to the I, P1 plus P2 times L is 1. So I can multiply the left-hand side and I multiply the right-hand side, which is equal to 1. So I get this equation here, and this is the momentum quantization. So what you can check is that this is indeed equal to P total. This you should check. Small exercise.
Sorry, I don't understand. You have one equation C, and you
Yes.
get two equations.
Yes, because you have two exponents, and each of the exponents should have the vanishing prefactor. Because if you have an equation of exponents which have lots of L dependence, like position dependence in there, then the coefficients of those exponents should already vanish, and this is independent of the positions.
Okay.
So it's a separate equation for each of the two.
Sorry, but doesn't the first equation show that the S matrix is independent of P2 and the second equation show that it is also independent of P1, so it's just a constant?
No, it does not. No. Rather, these equations, they couple values of P1 and P2. So it's really a coupled system of equations. And you can take one of them together. So this here is the momentum quantization, right? So this is our old equation, P total is equal to 2 pi over the length times some integer. But there's another equation which really says that these two values of P, they are now coupled. And this is important. So actually, let me say a little bit more about this. Well, I'll get back to that later, actually. But yeah, that's an important remark. So yeah, I'll get back to this in a second. So, okay, so now there are two little exercises. Okay, so first exercise is workouts, because I didn't really, I told you what the results are, and there are small computations to be filled in, so work out the details. And then the next exercise, so remember last time we did this free fermion Jordan-Wigner thing, and I said that if you're a bit of a masochist, then you can really do this even for X, Y, Z. So here's the exercise for masochists. This is repeat the whole same derivation for M is 3. And you can do it, but it's getting a bit worse. And of course, you need to know what the beta ansatz is. And in order to tell you, here you need to use let's say the coordinate beta ansatz below, which I will give you right now. But first, I want to ask you.
This is you saying coordinates, and maybe you tell us about it when you actually break down the coordinates is compared to momentum.
No, right. No, so there are lots of versions of beta ansatz. There's something called an asymptotic beta ansatz. There's one called an algebraic beta ansatz. There's this coordinate beta ansatz. There are many, many different versions. Some of them are really equivalent. Some of them are kind of applying slightly different contexts, but often they somehow share an idea. Here, the point is that we did everything in the coordinate basis, and then the version of the beta ansatz that you need to use is the coordinate beta ansatz. That's the reason for that. Okay, so I'm asking you to work out the details for MS2 and check that everything that I said is correct, but at least I want to, just before I mention the results for general M and talk more about the interpretation of all these things that we found, I would just like to quickly check if the idea, if it makes sense. So what we did is we had this wave function, we extended it first, not just to the intervals 1 up to L, but to any interval of length L in the integers. And then moreover, I formally extended the wave function to allow for equal arguments. It does not appear in eigenvectors, but it is much easier because it allows us to simplify the equations. So then we get simpler equations, but they have to hold for more values of the positions. So it's somehow sufficient but not necessary way to solve the whole system of equations. And then we kind of recognize that actually the equations look a lot like what we had for one particle. So it should be plane waves, but there's some interactions. So we account for all possible ways that we have these possible downspins. This reason.
If I understand it right, if you want to think of the constraint on a possible L pairs of P1 and P2.
That's right. So that's exactly right. Yes. So let me. So now this is the physically meaningful, which I will kind of talk more about later. Parameterization of possible wave functions by two parameters P1 and P2, and this is not always an actual eigenvector or an actual wave function, but it is when the ratio is given by this S matrix and when the P's, which are these parameters, have numerical values fixed by these equations. And then at the end, I will kind of say a bit about, can we actually solve these equations? Does it have sufficient solutions? Are all the, all these kind of stuff. But indeed, so this is really the first.
I mean, on the infinite chain, it's still a good wave function. You don't need the equation.
That's right. Yeah, it's kind of like a version of momentum quantization on the finite chain, but now for each of these p's separately. And now they kind of feed each other. They're not just free particles, but they. Okay. Let me try to keep this for a little bit.
Can you solve the equations?
I'll talk. So in general, I mean, these I understand extremely well, but beyond it gets much harder. I will tell you a bit about this later. And in particular, I will show why they're good. Because what we've really done, at least for M2 now, is we've kind of reduced the problem of diagonalizing a Hamiltonian to the problem of solving some equations, which may be better or worse. And I claim that it's actually better. And one reason why it's better is this phrase, which I will illustrate in a moment, that this parameterization is physically meaningful. So one thing that you can already understand is that from solving these equations, one thing that you can immediately make, and numerically, I do this up to like length, any length really, it's very easy to do. So note that the dependence on the length here is very mild. So if you have a ferromagnetic chain, then M is 0, we understood, this is the ground state. M is 1 is also, let's say delta larger than 1. So then M is 0 is the ground state, M is 1 are excitations, they're also very simple, and even M is 2 is, for any L, is still quite simple. So this is one benefit. And then the other thing that you see is that here, you have these P1 and P2. So you can kind of think of this, and we will see that this extends to general M, as quasi-momenta of the downspin. So you can really think of these downspins as kind of quasi-particles moving in the chain, and they each contribute to the total momentum, and they each contribute to the energy, as I wrote down there. So each of them has their own contribution to the kind of the physical quantities of the model. And one thing that it immediately allows you to do is you solve the equation for P1 and P2, and then you plug it into both the momentum and the energy, and this allows you to make a picture of the form. Here you have your P total, which is from 0 to 2 pi periodic, and then here you have your E delta, and I can just actually draw what this looks like. Whereas if you numerically, let's say, diagonalize the Hamiltonian, then you get the list of energies, but you don't know which momentum they correspond to. So then you have to really build the full vector and then act with the translation operator to read off the momentum. Or you have to simultaneously diagonalize them numerically, but this is not so good either. So here, I just have to solve some equations. I don't have to build the vector, and I can already draw nice pictures of this type. So this is one reason why it's super useful.
If you solve the equation, you find P1 and P2 with some relation, then you plug it into here and you get the energy.
Well, you find numerical values. You really find
numerical
exactly. And then you just put it in here and you get some energy, and then you put it in there and you get some momentum, and then you can check with numerical diagonalization that this is really precisely what you get. So even though these equations have to be solved, this is really an exact characterization. If you were able to exactly solve those equations, then you have exact energies. Well, exact momenta are easy enough, but exact energies. So this is kind of a nice feature of this business. So before I comment more on why everything is useful and what it means and so on, let me just outline what happens for general M. So the coordinate base ansatz in this case is, and I think hopefully it's not too surprising at this point, is that the psi, which depends now on, so now we take m different parameters p, so each magnon gets its own parameter, each downspin gets its own parameter, and then I parameterize the wave function as follows. I take a sum over all possible permutations, so let me call permutations W, all the possible permutations of the magnons, and then I have some coefficients, one per permutation, depends on P, this coefficient, and then we have e to the I P subscript W times L, and this P subscript W is just the vector where I've permuted all my parameters P. Right? So just like before, I took the two linear combinations of those plane waves that solved that already, that I would get from separation of variables. Now I just take all possible plane waves where I just move around stuff. And then, of course, things similar to here will happen. But now each particle has its own parameter P. Okay, so we proceed as before. So firstly, we know that the assumption is okay. Boring, but good to check. Then we have our equation A. And we will just check that this works. So it's okay. And we read off that the E of delta, which now maybe I can write down, is E of delta that depends on all these P's. And it's just the sum from little m is 1 to big M, so over all the possible downspins of their epsilon delta Pm. So this is an extremely nice result. We call this usually additive additive energies, but I want to emphasize that it's only functionally additive. So it's not true that if you really compute the value of P1 and P2 and so on, that's right. So here, if I actually solve those equations, then it's not true that the energy, if I would just do it for m is 1, and I compute this for a free magnon, and then I have another free magnon, if I put them together on the chain, they will interact a little bit because of this S matrix on the right-hand side, so their values will change a little bit. And so this here is not just the sum of the one particle energies. It's modified a little bit because they interact, right? So here, this is kind of like additive, but only as a function of P. So that's why I want to call it functionally additive energies. Functionally additive. Then we have this bounds condition B prime. And here, long and tedious computation shows that now ratios of coefficients, so A, W, B, and it's up to normalization. So let's divide it by the case where the permutation is the identity permutation, I denote by E, the identity element of the group. So this is really nice, actually. So it's the product over all pairs M less than N up to the number of magnons, such that W of M is larger than W of N. So all those magnons which have been swapped kind of by the permutation W. And then here, I'm just going to get S delta PM PM, and there is inverse. This inverse makes sense because here I compared the coefficient of the identity with the coefficient of the swap thing. So now I do the opposite, so I get an inverse there. And so this also has an extremely nice physical interpretation. So you can think of this here as factorized scattering. So the picture is the following, if you kind of think of this a bit. So we have some number of incoming particles, which have kind of parameters p1 dot 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 pm, and we kind of look at it from far away. So we have some scattering where now we have pw1, pwm. Then what it says is that this process in the middle, it actually factorizes into two body steps. So for instance, this could factorize by first the two on the right could meet, then the ones here, and then those there. Or of course, it could also happen the other way around. So they could also meet like this instead. And so these two have to be the same. It's a consistency condition normally in QFT. If you would do integrable QFTs, but here our S matrix is just a 1-by-1 matrix, so this is not really a consistency condition. But you know, it's super cool that what it says is that this sort of looks from far away process can really be decomposed into pairwise steps. So in other words, this is two body reducible scattering. So in terms of this language, if scattering were one body reducible, it means that nobody feels each other. So this is just a free system. Now we have two body reducible scattering. So this is kind of the next simplest in momentum space after a free system, where the particles interact, but only in terms of pairwise processes. So it's a very, very nice property. And maybe I should also write, so as I kind of already suggested, maybe it's this product here over all m less than n, such that they've been swapped. They precisely mean that if you draw your permutation, so we have some p1 dot 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 pm, and then here we have pw1 dot 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 pwm, and w maybe swaps it in some way. So maybe it keeps these and it's going to swap those and it's going to do this and I don't know, whatever. Something like this. I guess I should have pm there. WM. And then this product on the right-hand side has a factor of an inverse scattering matrix for each pair, like that. So very simple. If you think of this as a permutation, this is the number of inversions of the permutation. And then finally, we still have our periodic boundary conditions. So we impose them, and we get the following set of equations: e to the I p m little m times the length is equal to the product of all the other particles, so sum over n different from the m that we have on the left-hand side up to the number of megnons, and then we have our S delta Pm, Pn. And these are this should hold for all m, little m from 1 up to big M, and these are our Bethe-Ansatz equations.
In the condition, the prime, what is the subscript on the A downstairs? A L or A?
Oh, here, E, the identity, sorry.
Oh, the identity.
Yeah. Sorry. Identity element is a permutation that doesn't permute. Right. So this also has a nice kind of physical interpretation. Namely, if we imagine our chain, so let's look at it from the top. And at some site L, we have our downspin, which has momentum, parameter p little m. Then on the left-hand side, what you see is the eigenvalue of the translation all the way around. It's kind of like a shift all the way around the chain. So this is the phase that you would get if you're transported all the way around the chain. But on the right, what you see is, well, you have some other downspins sitting here and wherever. And what happens is that as this downspin is moved around, it kind of interacts, it hits, it scatters with all these downspins. So we get little kind of explosions, which each contribute to the factor of the scattering matrix. And the Bethe equations just say that moving the particle ones around gives the same phase as scattering on all the other downspins, so on all the other quasi-particles. Okay, it's just a sort of an interpretation, but I think it's a nice way to think of these equations. And as we already kind of mentioned before, is that you can also view these as quantization conditions. Conditions for the Pm. And of course, I should mention, which is easy to check from this wave function, is that, again, these equations together, they imply that P total, which is just the sum of all the parameters, should again be quantized as 2 pi over the length times an integer. Okay, so one of those, I mean, these are big M many equations, one for each downspin, and together they, like before, they imply this total momentum quantization. Total momentum by a separate computation can be seen to equal the sum of all these PMs. And to drive home this last part, let me write the bit equations in a different form, in a slightly different form. We'll define a function which is called the scattering phase shift. Which is, so I will denote it by phi subscript delta, and it only depends on two arguments, and it's just minus I times the logarithm of the S matrix. In other words, I write the S matrix is e to the I phi with this phi. So this is the phase corresponding to the scattering matrix. Then we get the logarithmic form of the beta ansatz equation. So I'm going to take the logarithm of the beta ansatz equation, and then what I get is the following. Let me write it in the following way. So Pm times L is equal to 2 pi times some integer which I call Im. So this is my integer in modulo L. This is the integer from that appears similarly to here. And then I'm going to get the sum of a half, I think, sum of all the n different from m up to big M of the scattering phase shifts, e to the I, p, m, p, n. So this is really just the same bit equations, but now after taking a logarithm. And here we see the interpretation a little bit more. Here we see that this, well, if I divide by L, let's do that. Let's put this in here. Let's divide by L and here as well. Then this part here is kind of like the bare value of the Pm. And these here are dressings, I don't know, like modifications due to interactions. And this is the real value of this Pm. And by the way, the Pm, they're often called quasi-momenta. So physically, what the results of this coordinate beta ansatz are very, very nice. It says that we have a parameterization by one parameter for each downspin, and we can really think of this single parameter as the contribution of the downspin to the momentum, because we have this sum here, to the energy, because we have that sum there, of each downspin separately. So that's why they're really the momenta, the quasi-momenta of those quasi-particles. And their values, well, they're not quite 2 pi over the length times an integer, but they feel each other's downspin, so their values are modified away from their values if they would have been free particles through the scattering phase shift.
Sorry, are the phi delta well defined? I mean, log is maybe multi-valued.
Right. So you have to
fit some cut.
So if you want to look for this in the complex plane, then you have to think a bit carefully about how to do this and so on. Yes.
In the case of particles, it was a direct consequence of various equations that
Yes.
Is it also easy to see in the case of general number particles?
Yes. So these scattering phase shifts, it is so okay. So if you look at this S matrix, you see that if you swap P1 and P2, then you change the numerator and the denominator. So S with swapped arguments is the inverse of S, which means that this phi is anti-symmetric function. And so it means that if you add this over all the m, then the contributions here will vanish because it will occur twice, once with one order and once where they're in the other order. And so this disappears, and then you see that the integer that I had here is just the sum of those integers that are modulo L. Very good. So, and these integers, they're called sometimes the beta quantum numbers, or beta integers.
Sorry, just.
Yeah.
On this equation C, it looks like if I take Pm to plus or minus 2 pi over L, it's invariant. I mean, what you have with this integer here, it's like if you add 2 pi over L, it doesn't change much for the.
This equation C?
No, it's above.
This, yes?
On the left hand side, if you take Pm to Pm plus 2 pi over L, it doesn't change.
Yes.
But for the S matrix, it's not obvious that if you change. Is it 2 pi over? Is it periodic in the piece somehow, or?
Right. No, I mean the scattering rate, we see that it has a period of just 2 pi per variable. So these equations kind of, on the left hand side we have something which indeed is 2 pi over the length periodic per variable, and on the right hand side we have something that is 2 pi periodic. So it really, this is part of the sort of the constraints on the values of these feeds. Yes, that's true. That kind of mixes different periodicities, but it's still, it's a no problem. It's what it is, indeed. Yes. So if you are okay with it, I would like to just go on for 5 more minutes, because then I can finish the part about the coordinate beta ansatz, then we can have a little break, and then I will tell a little bit about a different topic. Because I just want to say a little bit more about, is this useful, or what is the physics? Actually, let me keep this. I really need it. Here, I wrote down what it does as a matrix, but now we know what it does on the wave functions. So that's fine. Okay, so there are a few exercises and a few kind of remarks. First exercise is that you can check that this beta wave function, as it's called, vanishes if 2 of its parameters coincide. So this is like a Pauli principle. It says that the quasi-particles are not allowed to have the same quasi-momentum. So this ends their purpose. But remember, we're in 1 + 1 dimension, so with bosonization and so on, so they may have kind of properties from both sides. Now, an important question is, okay, I said what we did is we wanted to solve find the spectrum of the Hamiltonian and its eigenvectors, and we did a parameterization in terms of this wave function. And then we wrote down some kind of stronger conditions, and we said, okay, so if we can solve all of this here, then definitely we should find a wave function, provided the result is non-zero. So the question is now, are really all wave functions of this form? Or maybe there are other vectors which are just completely not described by this thing here. And so this problem is called completeness of the beta ansatz. And in fact, this does give all the eigenvectors. All eigenvectors. The Hamiltonian. And this was, so maybe it's surprising. So I mean, there were some, there were partial rigorous results and so on, but this result is due to Muchin, Tarasov, and Varchenko. And if I'm not mistaken, it's from 2009. So it took more than 70 years between beta and the actual proof. I mean, people, of course, did numerical experiments long before and all sorts of other things, but really the proper mathematical proof that this is really gives a complete description of the spectrum is very, very recent. And they actually found this first for a simpler model, which is the Godin model. And this is also closely related to geometric Langland and all sorts of stuff like that. So somehow it is really related to deep mathematics. Very nice stuff there. Okay, so to do is we need to find all corresponding solutions to the Bethe-Ansatz equation. Corresponding to linearly independent eigenvalues. So some little exercises. So usually this is very hard, but what you can do is you can solve it for delta 0, which are pre-fermion points. So it should be very simple. You see that the S matrix simplifies a lot, and in this case you can actually just solve the question. Nice and easy. Another little exercise is remember our other simple points. So we can also send delta to plus or minus infinity. And now this is not going to give you all solutions, but assume that those parameters p, they're real. All. So if you assume this, then you can also solve the equations in that way. Okay, and then the last little bit is just really illustrates that this is useful. Okay, so in general, solving the equations is hard. So you can do numerics and so on. But the nice thing is that you have these integers, these IMs, these Bethe quantum numbers. And so if you look at the logarithmic form of the Bethe equations, then you want to fix some value of the integers and then find a solution corresponding to it. So you can try to use this, that's why they're called quantum numbers, to parameterize different solutions. And then the question is for which range of integers will you get the solution and what does it look like and so on. And this is a hard problem. But what is extremely nice is the following fact. So it is kind of physical, so it gives nice information. And so if delta is smaller than 1, then the anti-ferromagnetic ground state, so this is work of Young and Young from 66. I guess I should also write them down. So the first one is the Young-Mills Young, and the other one is his brother. In 66, they proved rigorously that there is a class of solutions to the Bethe-Ansatz equations where these integers are well separated. So if these integers are not equal and are not adjacent, but they're really well separated now in momentum space, then you can show, they prove that there is a real solution to this equation where all the values p1 up to pm are all real. And in fact, the scattering phase in this case is very small. So you can really interpret this as essentially almost free downspins moving around the chain, and they interact very weakly for small contributions here, but this is very small. So these integers really tell you very precisely where to find the values of these quasi-momenta. And in particular, if I take my integer to be 1, 3, ... all the way up to L minus 1, okay, so I assume that L is even, and I am at M, the equator, so L over 2. So this is where the antiferromagnetic ground state occurs. It's not up, down, because, you know, there's some hopping and so on, so it's some sort of correction to this alternating state. And with these integers, you now find a solution. There's a unique solution Pm, very close to 2 pi over the length times the corresponding integer. Pm is real. And so you kind of think of it as a Fermi sea. This is kind of like a maximally filled kind of a ground state, and then you can take particles out of it, and you can start moving these kind of integers around to get excitations on top of it. But so it's very nice because inside this huge kind of Hamiltonian, we can really neatly specify how to find the ground state. And solving it is numerically very easy because in this case, everything is real. So, you know, in Mathematica, you can do this up to like, I don't know, arbitrarily, I can easily do it up to probably 900 or whatever. You can really go very, very far, no problem. And then you really find the energy to as high a precision as you want to solve your equations. You find the momentum corresponding to it. It's very easy. It's actually, well, you can compute it. They contribute L to the, or 2 pi to the momentum, so you can kind of remove them. So depending on whether L is a multiple of 4 or not, it's pi or 0. That's also a bit of exercise. But so the beta ansatz is very nice because it gives an extremely clean and physical characterization of the ground state. And moreover, if you remove one of these integers and then you can move around, there's a little kind of gap in there, so you can move around the integers a little bit. These are the lowest excitations around it. This is 2 spin-on contributions in physical language. And then you can go one step beyond. And that's what people did numerically to then make those connections to experiments. Okay, so I hope that this gives some sort of use of the beta equations. That even though the equations are hard to solve in general, they have very nice physical kind of structure. And if you want to understand them in great detail, this is hard. Certainly if m is 3 or onwards. But, you know, it's much better than just kind of brute force diagonalizing. And moreover, you get energies and momenta and so on all at the same time. And you don't even have to build the eigenvectors if you don't. So that's one.
When you said that the article was rigorous, you mean that they control the remainder, the difference PM minus 2 pi over L. They have a bound on the.
So what they do actually is they show that there's a function. It's called the Yang-Yang action or Yang-Yang functional. Yeah. And these equations, it's a function of n different variables at these, and its derivative with respect to any of these. So its saddle points are precisely described by these equations. Okay, so these equations are precisely the derivatives of that function with respect to each of the different variables. So you have some function. If it is a function just on the real axis, then you can check that it's actually, you know, it could be a saddle point or a maximum or a minimum. But you can check that this is really a minimum of the functional. And then what you also have to check is that the solutions don't kind of run away to infinity, because, you know, if you have like an exponential is also a convex function, but there the solution runs off kind of to infinity, so it's not so good. So what they really do is they check by analysis that this is the minimum of some functional, and that it doesn't run away to infinity. And that's how you can prove that there exists a unique solution, which is precisely at the lowest value of the functional. And then they use this to compute free energy and all these kinds of things. It's a series of papers, but it's very nice. And actually, this kind of statement is also true for as long as these integers are separated, the same convexity argument works. However, if you do the counting, you will see that these well-separated integers only gives Fibonacci in M many solutions, so it's less than the number of solutions that you really want. And so, in fact, all the other solutions will have complex values of the PMs. And then by reality of the energy, you will see that they must come in complex conjugate pairs, and this corresponds to bound states, where the bound states are kind of tend to be very close to each other. And if you take the Ising limit, then you will see that they're really actual sitting next to each other. And in general, there are some corrections to it because of, you know, finite delta effects. And so the difficult part, if you want to really understand the full spectrum, is to control all the which possible values of the integers, including adjacent or equal integers, appear. But you know, that's just not solved. All right. So sorry for going over time a little bit, but this is the coordinate beta ansatz. So now we'll have a little break, and then afterwards we'll look at something completely different.
Maybe it's a good time to ask questions.
Absolutely, yes. If there are more questions.
Maybe I have a comment. For the student should really do the n particle, because you learn something if you do n particle. In particular, you see that A of P, the ratio of the amplitudes, you just need to permute two neighboring permutations. So I mean you get some relation between. So that's why this relation comes from making a lot of small permutation. I mean, just not.
Yes. So in fact, you will already see it if you do this exercise here. You will see that there are 6 terms, and you group them into 3 and 3, and they nicely combine to give this result. It's a use function, but it's a little bit painful. It's a little bit painful. So what I think that this. You know, this
in the book of Godin. You look at in the book of Godin, first chapter.
Yeah, it's very true. He's very quick at it. This is true. Right. But kind of to do it for yourself, it requires some work. So I think this part, the coordinate beta ansatz, in some sense, is a little bit painful, but it's kind of like a, you know, like an initiation, right? Once you go, this is kind of some pain that you have to endure to get into the field. And one of the things that the course that we will do later on is we'll go after the break, we'll go to another model, which seems unrelated, but turns out to be related. And that will give us somehow the way into really a nice mathematical structure underlying all of this. And we will be able to redo this. We will get all these results in a much simpler way in maybe 2 lectures or something, using a bit more algebra. So, and maybe what I should also kind of say is that even though the computation is a little bit painful, the outcomes are very nice and very physical. So we get this quasi-particle picture. And maybe I should emphasize that these quasi-particles, they have lots of their sum of the p's are conserved. The sum of their little energies are kind of conserved. We have this factorized scattering. So in some sense, these downspins, they interact, but they do so with a lot of kind of constraints. There are a lot of kind of things that are conserved, and then they have a lot of nice properties. So if we want to think of these quasi-particles as kind of people, then these people are very polite. They kind of interact with each other, but they shake each other's hands. They might delay each other a little bit, but they don't really do anything brutal. They don't kind of smash into multiple pieces or merge or something. They just they interact a little bit and then they go on along the chain. And so this hints, physically, you would expect that this tells us that there should be underlying extra symmetries. There should be more than just momentum and energy that are conserved, because the interactions are so kind of constrained that there should be something extra that constrains it. And so that's really where the quantum integrability, will be the quantum integrability giving all these extra symmetries. So really, that's actually it's good.
Isn't it obvious that some of the ki to the power n is conserved already? I mean, it's clear.
No, I don't think it's obvious to me, but maybe it's obvious to you. In integrable quantum field theory, there's a nice argument where you can show related to so there you also have this factorized scattering, and there you can show that any polynomial in the p's. But here, we're working with cosines and so on. I mean, it's kind of trigonometric. I don't know.
No, I'm sorry, because I think of the other model.
Right. So in like things Gordon and so on, and that's precisely what happens.
Cosine.
You're online.
We're online? Okay, very good. So then let's continue. Right, so excuse me for going over time before the break. I will go under time now, so then hopefully in total we're pretty good. So maybe what I wanted to kind of conclude the last little bit by is that so Feynman, towards the end of his life, became quite interested in this coordinate beta ansatz. And if you look online, there's this, this last blackboard of Feynman, and you will see that beta ansatz is among the list of things that you would like to learn. And since anything becomes more cool if Feynman has worked on it, let me just mention that he has there's this quote by Feynman who says, I got really fascinated by these 1 + 1 dimensional models that are solved by beta ansatz and how mysteriously they jump at you and work and you don't know why. I'm trying to understand all of this better. So, if Feynman would have lived another 5 or 10 years, then maybe he would have been the one who really made the big breakthrough in the field. Now it was other people, maybe a little bit later, but not too much later. And now we're going to go slowly towards that. And we'll do that by taking a detour through a seemingly completely unrelated model. So today I will just introduce this different model. And then next time we will slowly start to uncover how they are related. So this is part 4. The model is called the 6-vertex model. And it's also called an ICE-type model. So to introduce a model, let's call this section ICE and its friends. So if you get something slightly more golden now, then it will be freezing outside. And the normal water ice, I'm just thinking of H2O. So an ordinary, and chemists call this 1 H ice. In this case, the H2O molecules, they form a hexagonal crystal. That's why the H. Actually, if you go on Wikipedia, so you'll see that there are lots and lots and lots of different phases of ice. You know, there are like 2 and all sorts of strange things. But 1H is almost all ice in nature. And it is hexagonal ice. And what that means is that the oxygens form an hexagonal crystal. So let's try to draw it. So it means that if you take a single oxygen, then its nearest neighbor oxygens will be at the vertices of a tetrahedron centered at that oxygen. So let's first draw a tetrahedron. And we put a single oxygen in the middle. And then we put its nearest neighbors on the corners. And then you could continue this picture. And then we know that there are hydrogen bonds between these oxygens. Let me actually draw them in a different color. Take a nice blue. So these are the hydrogen bonds between the oxygens. And almost, like to a very high degree, this stuff is electrically neutral. So electric neutrality. What it means is that on this hydrogen bond, there's a single hydrogen atom, and so proton. And the proton is, there are always 2 protons close to the oxygen and 2 farther away. So for instance, maybe here and here, there are the 2 protons, very close to one side and very far from the other one. And then actually, let's extend this picture a little bit by drawing the lines starting out to adjacent oxygens, all these other guys, I don't know, something like this. Then since this one, so on this edge there should also be a hydrogen, so it's here, and this one is here. But then this oxygen has 2 hydrogens close to it, so maybe it's here, and then maybe this one is here, and maybe these are there and there, and these could be, I don't know, here, like that. But this is what the crystal of ice looks like. 1 proton per hydrogen bond, and 2 hydrogens near each proton. Okay, so this course is about quantum integrable systems, so 3-dimensional is not good. We have to squeeze this picture, and so what we'll do is exactly that. So we'll do a 2-dimensional approximation to this. So we start from a square lattice. Because the oxygens, so we look at this kind of blue thing and we kind of flatten it. And now I'm going to draw. Okay, so if you have lots of colors, then it's good, because I'm going to use lots of colors. Alternatively, you have to draw the same picture many times or think about how to do this. So I'm going to draw and keep some space around this. 6 different configurations like this. I mean, parts of this square lattice. Right, so we have a square lattice, so we have a grid like that. And now I'm going to zoom in on this here. And so we think, firstly, that at this vertex is where our oxygen is sitting. Then the reason that I drew 6 different pictures is because we have 6 different ways that these hydrogens can be arranged around the oxygen. So let me draw them, and be careful to draw it in exactly the right way, because it's good to label stuff later on. So the protons can either be to the left and below, or to the left and above, or to the left and the right, on the top row, or they can be on the right and above, or on the right and below, or they can be above and below. And then, of course, if the next oxygen is here, then this hydrogen should be there and there. So I'm just going to make sure that there's 1 proton for each of these hydrogen bonds. Far away from the oxygen now. Big neutrality. So we have these 6 different pictures. Okay, so these pictures are kind of a little bit annoying to draw. So let's simplify our life a little bit and replace this picture by just putting a little arrow which points towards the hydrogen. So here, the arrow on the edge is going to point to the side that the proton is on. So here they point to the right on the horizontal edge and upwards on the vertical edge line. Here, well, you can do it yourself. So it's still to the left, but then down. Here it's horizontally inwards and vertically outwards. And then here they're kind of flipped with respect to there. Okay, and so what I'm actually going to do with different colors is I'm going to draw the same configuration in many different ways because they give many different interpretations of this whole story. So let's remove this and make a little table. So
Did you say why you call it hexagonal?
oh, because well, if you continue this thing here, then the kind of the dual graph, I guess there's a these things here they're going to form hexagons. These blue lines. Keep really close to it. It's a little exercise in discrete geometry. You can mentally kind of almost see the things later. You know, this is going to go away and then up and then going to come forward and meet with this guy here.
It's not a plain hexagon.
No, right. Yeah, no, really, unfortunately. Okay, so let's make a little list on the left. So we have our local degrees of freedom, which are sitting on the edges. And then we have our local constraints. Which is at the vertex. So we have many different ways of thinking about this. So the local degrees of freedom here are our proton configuration. Right? So we have our edge, and then we have this little guy sitting there somewhere. And our local constraint is this electric neutrality. So precisely 2 protons close to each oxygen. And in terms of the arrows, well, we have an arrow configuration. And then if you think of this as kind of like a discrete vector field, then it is divergence free. Equally, at each vertex, equally many arrows point in and out. So these arrows are already a bit more efficient to draw than those protons, but they're still a little bit too much work. You can imagine if you have a big grid and you put lots of arrows in it everywhere, then it's kind of hard to see what's really going on. So another much more simplified version is to draw paths instead. So let's pick this configuration here in the left top as our kind of reference configuration, and we say that this is kind of like empty. And now what I'm going to do is I'm going to take my next color, which for me happens to be orange.
Sorry, what is the divergence?
All right, so the local divergence here is the number of arrows coming in and the number of arrows going out. If you think
Okay.
of this vector per,
So 0, okay.
Yeah, yes, so 0 divergence. Yes. So now what I'm going to do is I'm going to either fill the edges or not. So I'm going to draw like paths on this lattice. Here, by default, this is empty, and then in all the other things, I'm going to just color edges that differ from this reference thing here. Okay, so here, I have to color this line. Here, I have to color this line. So any arrow that goes to the left or down has to be colored. So here, everybody gets colored. Here, the horizontal one gets colored. And here, the one coming from the, like this, gets colored. I hope it's visible. A little bit more thick. Note that the top and the bottom differs in kind of blue versus orange. If I would swap blue and orange, then I swap the top and the bottom here. So now I have path configurations. But not all possible paths are allowed. So only those paths are allowed so we'll call this path, or sometimes line conservation. And for this, we have to be a little bit more careful. Not all possible paths appear, but the paths they're supposed to go from the southwest to the northeast. So kind of generally they have this direction. Okay, so I think of it here, there are no paths. Here there's a one path coming from the bottom, exiting at the top. Here it comes from the bottom and exits on the right, and so on. And then these paths, you know, they can change direction at the vertex, but they have to continue. You cannot they cannot just stop, or you cannot create a path out of nowhere. And then here you can think of this as either two crossing paths, or you can think of it as two paths kind of bouncing on each other. So sometimes it's oscillating because it is in the center.
I mean, but that this is a convention. They are
This is a convention.
oriented.
Absolutely. Right. So for this, that's right. So it's a convention, but it's, you see that it's just an equivalent way. Instead of all these red arrows, I can just do these paths, and then the paths are easier to draw and easier to interpret. You immediately see what's going on. So it's just a, but indeed, it requires on the convention of thinking of this as going from the southwest to the northeast. So indeed. And then one more way to interpret this thing here is I can think of these arrows as on the edges. Yes.
It is not clear to me that given a configuration of paths, there's a unique choice of the arrows that you can. That needs to be the case, right? Bottom right, you could put the remaining arrows in the opposite way. It would still be.
No, because the path kind of is what the path does is it marks the difference with respect to the reference arrows. So I define this to be kind of my reference arrows, and then the paths just color everything that are not all the arrows that do not match this here. And it's really a bidirection. Yes. But this interpretation requires fixing something as reference, so I chose this one. And moreover, to think of this as kind of conserved paths, I have to kind of think of some sort of general direction that these paths have to go.
As you say, also you follow the arrow going to the left and down.
Right, so you can change different orientation, and then you would have different looking kind of path picture. But yeah, so
from right and to the top, but that's a matter of choice.
I prefer this one. All right. So one more thing that will be useful for us is we can, rather than these arrows, we can kind of think of them as kind of classical spins, and then we can also denote them by pluses and minuses. So now I'll think of on the edges, but I'll draw them on the left. Here I have pluses, and then so I'll draw pluses whenever there's kind of an empty line, and minuses whenever there's a path on the line. So that's yet another way of thinking about all this stuff. And in this case, we have, well, this is kind of like a classical, so an Ising type spin. I'll put it in quotes because it's not at all a quantum mechanical spin, it's just a plus or minus variable. And so we have classical spin configuration. And then the rule says that spin is conserved. And now I want to emphasize, Ricardo already mentioned, that these two pictures, they kind of rely, so here we, for the language of conservation, we orient the lines. So say we think of all the lines as going in the lattice, going to the, oh no, this is the wrong color blue. Say they go to the right and they go upwards. Okay, so this is the orientation of the lines, and that's the orientation that these paths are supposed to follow, and it is the direction in which I can measure that the spin is conserved. So here I have plus plus coming in, so plus plus come out. Here plus minus is coming in, so they can either swap or not, and so on. Okay, so lots of different ways to think about the same model, and in all cases, you have these 6 different vertex configurations. So now, let's make this statistical mechanical model. So in StatMech, this, as I already mentioned, it's called the 6 vertex, or also ICE type, because it's kind of like well, it was motivated by ice, and it has 6 vertices. So pretty easy model. So what we do is we give each configuration an energy. So configuration in whatever your preferred language is. And the rule, which is kind of the rule for what are called vertex models, is that it's a sum over vertices. So you distribute all the possible vertices in your lattice, and then you assign a local energy around this configuration as a vertex. So it is the energy of our kind of hydrogen around the protons kind of.
Sorry, I really don't understand the spin conservation. I mean, when you have 4 pluses, how do you?
So, right. So I have to really think about this orientation of the lines, like here. So I
the
think
blue lines or the orange
the
line?
blue lines are oriented from the left to the right and from the bottom to the top. So then 2 of them are incoming, namely the one on the left and the one on the bottom, and 2 are kind of outgoing, namely the one on the top and the right. And the number of pluses and minuses, so the total kind of charge or spin or whatever you want to call it, is conserved in this direction. But it totally depends on the convention in which you define your orientation.
Okay, now I see it. Okay, thank you.
All right. So for vertex models, the energy is given by the energy at the vertex. Let me call this epsilon, the local energy at that vertex. And then it depends on the configuration just around the vertex. In other words, to each of these 6 configurations that I drew, we assign some local energy.
By around, you mean nearest neighbor?
Touching the vertex. Yes. So then, in statistical mechanics, we define beta to be 1 over the Boltzmann constant Kb times the temperature. So this is the inverse temperature. And we define the partition function to be the sum over all possible configurations. And then we do e to the minus beta energy of that configuration. And the partition function is nice. One of its uses is that you can now define a probabilistic model. So you can give the probability of finding a given configuration is 1 over the partition function times the this Boltzmann or Gibbs measure kind of thing. This is basic mechanics. We have the canonical partition function here. Now, of course, writing this e to the minus beta, blah, 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 is all a little bit painful. So let's give these guys here names. So we'll call this configuration A plus, this one A minus, this one B plus, this one B minus, this one C plus, and this one C minus. And in my convention, the plus or the minus is the classical spin on the left. That's just okay. So these are the names of those vertices. But I will, okay, maybe slightly abuse notation. So let's also define vertex weights. So we will get, for instance, e to the minus beta and then the epsilon of the configuration A plus. Right? This will occur. So let's just call this whole thing A plus. Okay, so I'll kind of, so the vertex of that I called A plus also has weight A plus. Maybe I should have used different fonts, but I think it will be clear when I'm talking about a vertex and when I'm talking about a weight. Okay, so what we will do, and so on. So then, moreover, what we will do is we will focus on what is called the zero field case, where A plus and A minus are both equal to A. So these e to the minus beta, blah, 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 so it's equal to just A. Likewise, B plus minus equal to B, and C plus minus equal to C. Okay, so I say that the weights of these pairs of vertices are the same. Then with this assumption, this partition function can be written as the sum over all possible configurations of A, the vertex weight, times the number of A vertices. So this is my abuse notation. This here is the weight, and this here is the name of the vertex. I hope it's okay. Then B times the number of B's, and then C times the number of C's. Right? This is just what you get from here. And this gives us a statistical mechanical problem. So we want to compute this partition function. Goal compute Z. And okay, we have to be a little bit more precise if you really want to do this. So let's, what we will do, so we will take a K by L lattice on a torus. So we impose periodic boundary conditions in both directions. So I have some K horizontal lines L vertical lines, and it's on a torus, so I'll kind of indicate with little hooks that they're kind of, these are the periodic boundary conditions, and likewise in the other direction. Right, so I hope the picture makes sense. There's some partition function on the torus. Maybe I should add a few more in one direction just to make sure that K and L are allowed to be different. Okay. So I'm nearly done. Let me just mention some special cases which appeared before this general fixed vertex model was defined. And some special cases. I'm not right here, maybe a little bit too low. Let me do it here. That's good. No, I want to keep that as well. Okay, I'm just going to move this stuff. Now, the only thing that we need to know is that this is the partition function. Okay, so special cases. Just for historical name reason, it's good to give some names. So the case where these vertex weights A, B, and C are equal, so each of these configurations is equally likely, this is the actual ICE model itself. So not ICE type, but just ICE. But notice that if the temperature is infinity, so this beta is 0, then they're also all equal. So this is also the temperature is infinity point, which is kind of funny, right? ICE is somehow also the same as infinite temperature, but I hope that it's clear what it means, right? You either take whatever energies you want and send the temperature to infinity, all the weights will become equal, or you just take the weights to be equal, and then we get our original ICE model where we really didn't care how they were distributed as long as they obeyed the local condition.
Which is very bad.
Sorry?
You are icy when you're.
Yes, yes. Then another special case is where A is larger than B equal to C, which is equivalent to B being larger than A equal to C, by some maybe rotation or whatever, flip. This model is called, was studied by Slater or proposed to be, so it's called the KDP model. And this means potassium, well, okay, let me just, so potassium, okay, dihydrogen, H2, phosphate, SO4. So that's really the chemical compound that it describes. And the reason why it has this name is that this is a ferroelectric material. So the idea is that if A is larger than B, so these and these configurations are the most likely, which means that spins are, they tend to be maximally aligned in some direction. So here, horizontally, they either point the net kind of polarization at the vertex either points in that direction to the top right or to the bottom left. And now you see that I could have also chosen here instead. It's kind of bottom right, top left, so it's equivalent, but so it's kind of maximally polarized. Whereas the other case is where A is equal to B, it's smaller than C. And this is what's studied by Rees, and it's called the F model. I don't know why it's called the F model. And this is an anti-ferroelectric. So if you have a material where the consisting of little classical dipoles, and the dipoles tend to have, well, it's kind of staggered, right? So in this case, the C vertex is dominant. So what you see is that the spins, these kind of classical spins, they tend to alternate. There's some sort of staggered polarization. The net polarization at the vertex tends to be 0, but instead, if you count, well, some sort of staggered polarization, you'll see that this tends to be large. Okay, so let me give a little bit of a homework exercise. I'm going to uncover this in a moment, but I first want to write an exercise. This is kind of a fun combinatorial exercise. So let's assume that K and L are even. And let's assume that A and B are both much lower than C. So it's sort of an extreme version of the Rees model, except that I allow A and B to be different because it doesn't really matter so much. So then there are two ground states. So let's have a quick look at this again. So our C vertices are by far the most likely. So we want to have as many C vertices as possible. Now you can see that what you can just do is you can stack these on top of each other alternatingly, and also alternatingly from the left and the right. So what will happen is that you get this sort of checkerboard of staggered configuration, which is good, right? It's anti-ferroelectric, so it's sort of maximum staggered. So we have a checkerboard of alternating C plus and minuses. And in terms of the paths, which I drew in which color? Orange. So one example, okay, I have to draw K and L even. So 1, 2, 3, 4, let's say. 1, 2, periodic boundary conditions. Blah, blah, blah. Let's redo it. So what happens in terms of, remember, the C vertex meant that the path turns. In terms of the path picture, what you have is there's some path coming in, then it turns. Then periodically it comes out here, then it turns, and it turns, and then it turns, and then it goes there, and then it goes there, and up, and up, and it goes back to itself, and that's the configuration. Of course, I also have the path which is translated by one. If I kind of flip which edge is kind of occupied by a path and which one is not, it just amounts to swapping C plus and C minus, or reversing the arrows if you do the red picture. So anyway, I have two of these ground states. So now what you can do is you can kind of start from this ground state and kind of perturb away from it. And in this way, you can compute the partition function by computing only half of the partition function around one of these ground states. And the exercise is to check that this starts as follows. So I will, without lots of generality, I'll take the C vertex to be 1, just to avoid having to write lots of C's. You know the total of here, right? There are K times L vertices. So if I tell you all the A's and the B's, then you can work out how many C's there were. So then the ground state contributes 1, only C's. Then you get, so let me define N is the total number of sites, K times L, the volume. So then you can do a nice asymptotic expansion that you get N A squared B squared plus N times A squared B squared times A squared plus B squared plus a half N plus 1 times A to the 4th B to the 4th. And we can do one more. There's also N A squared B squared A to the 4th B to the 4th. And then you get higher order terms of higher degree in A and B. So you can really do this, and the nice thing is to do this graphically. So you kind of, so now this path will become very easy. So you can think, what is the simplest variation that I can do of this picture? What is its contribution? How many possibilities there are to do so? What is the next thing I can do? And so on and so on. And you can perturbatively compute the partition function in this way. So it gives a really nice feel of kind of how these paths, or any of your other favorite versions of the configuration, how it
It is a perturbation, really.
Right.
The partition function, when we do all the configuration, you round down the perturbation.
So the dots is higher degree in A and B, so lower order in A.
Okay.
So here's total degree 4, total degree 6, total degree 8, total degree 8, and then I think the next one is probably going to be total degree 10 in A and B. And yeah, so it's a nice combinatorial exercise. It's fun. Okay, so then the final thing that I want to do today, I want to say, so this is the 6-vertex model, but if you look at these configurations, then from this story about ice, this makes sense, right? We had these 6 possible configurations around here, so we model them in 2 dimensions, and that's it. But if you look at the path picture, for instance, it's slightly sort of unsatisfactory that the path, they're allowed to turn in this way and in this way, but they're not allowed to turn kind of just in any old way. So let's see what happens. So this is the 6-vertex model here. And now we're going to add 2 more vertices, and we can draw them in all possible ways. So let's draw, oh, this should be the good dark blue. Okay. Okay, so first in terms of paths, it's simple to see. So we're going to, so I said I'm always going to have the empty path here. So if there's an empty path here, it should now go down. So the path would be here. Oh, I'm not able to even do this. Okay, there's a path here, and it goes like that. Very good. And then there's a path here, and it goes like that. Okay. So that is the 2 extra configurations in terms of the paths. And in terms of paths, this is totally reasonable. In terms of the spins, which were green, what this means is that here we have a plus and a plus, sort of incoming with respect to our kind of fake orientation that we chose, and then a minus minus outgoing. So you see that this kind of changes the charge all of a sudden. So this breaks this charge conservation, or classical spin configuration. And here instead we have minus minus and outcome plus and plus. In terms of the arrows, so empty paths are going to the right and up, so we can draw them, and then filled paths go to the left and bottom. Those. So you see that this one here, it corresponds to a sink of arrows, and this one here corresponds to a source of arrows. So you see it breaks the divergence free. In terms of the good old ice picture, what it means is that now here we have 4 protons sitting right around the oxygen, or we have 4 protons sitting very far away from the oxygen. So it breaks electric neutrality. And in terms of the green language, it kind of breaks the spin conservation. Or instead you want to think of these pluses and minuses as, let's say, I mean, these paths, you can kind of think of them as like empty and occupied things. So you have some sort of particles on the lines, and it violates particle conservation. And this should remind you of something. This is a little bit similar to how the XYZ spin chain had, creation of pairs of downspins or annihilation of pairs of downspins. So in fact, this model here is called the 8-vertex model, if you take all 8 of them together. It's also an integrable model, but it's much harder than the 6-vertex model.
So is the 6-vertex model integrable only if A plus equal to A minus, or can you put arbitrary choice of the 6?
Right. So this depends quite sensitively on your choice of boundary condition. So, for instance, what you could also do, so here it's periodic, but what you could also do is you could either say that it's kind of open, maybe it's free boundaries, the boundaries can do whatever they want, or maybe you want to fix the configuration around the boundary and then compute your partition function. And for those fixed configurations, there are some sort of simple rules that account for that fix the total number of maybe C vertices that can occur. For instance, if you have a number of lines coming in from the right and a number of lines coming in from the bottom, then you know how many lines are going to come out at the top. So it can kind of tell you something about the number of C vertices. Because if there are more lines coming in from the right than going out on the left, then you know that they must turn up somewhere. So you know something about how often C vertices. And so you can use some of these symmetries. So I think you can set A plus and A minus probably always equal to each other, but the other ones not quite. And actually, I don't know off the top of my head which ones are integrable and which ones are.
When you say A,
Yes.
A, the exponent A, the sum of A plus A minus.
Ah, right, yes, perfect, yes. Very good. So let me actually write this more. So the number of A plus M minuses, the number of B plus M minuses, the number of C plus M minuses. Yes.
That means 4.
Very good. Yes, so I just call this a vertex of type A, and then count all the number of vertices of type A. Then here the number B, C. By the way, these are called D plus and D minus.
And the A square contains all
And the number.
the A square in your calculation.
Right, yes. And here I don't. So in this exercise, I did not distinguish between the top and the bottom element. Yes. I mean, you can refine it. You can do the perturbation theory separately in A plus. Probably it splits up into I don't know, maybe a product here, and I don't know. Okay, so this is the model. It looks quite different, but next time we will see that it's actually quite closely related to this XYZ spin chain. And the partition function can be computed using ordinal data. And moreover, the sigma vertex point of view really will help us developing the algebraic kind of stuff that I mentioned, which will allow us to do beta ansatz much more simply later on, to find all these hidden symmetries that's sitting behind the particles behaving so politely for the XYZ spin chain, and so on. So that is that's kind of the plan for the next times. But this is all I wanted to say. Any questions?
I have a question actually about the special cases here. I'm not sure I see this KDT. If I take B and C equal to 0 and A very large.
Oh, they're weights, so 0 is not so good, right? Let's take them 1. Write the exponents, and your multiplicative.
Okay, but I mean, okay, then I take A to be 1 and B and C very small.
Yes.
Then I will have basically only A's.
Yes.
So I can have either lines that cross.
Right. So one ground state is all the arrows point to the right and all the arrows point up. So it's maximally polarized.
Yeah.
Or it could be the other way around. By the way, now you kind of understand that this assumption here is called the zero field assumption, because if you would have some sort of external magnetic field, then it would break the symmetry between everybody pointing in one direction or everybody pointing in the opposite direction. That's right. So this is maximally polarized in terms of these red arrows.
Yeah, I could also have, like, if I have just one. Does it have more energy if I have just one cross? Like there is one line like this and one line like
Right.
this.
So then, so this is kind of right. So.
And my question was actually that this is very different to me from the other thing that you wrote, where B is very large, because then it seems that the lines can never cross.
Okay, well let's do it. So here is. So let's draw the letter dots. And let's try to think about the ground state. So this is a ground state for this KDP business, whereas the ground state for the other one like this, right? Here everybody is A plus or maybe A minus, and here everybody is B plus or maybe B minus. So you see that the two, I mean, if I want to do, so how do I perturb around this? Well, I have to create a line somewhere. You see, if I'm going to create a line somewhere, it has to go somewhere. So this perturbation is going to be kind of macroscopic, and depending on whether B and C and blah, blah, blah. So
there is a kind of
the best that I can do is maybe, for instance, this. So this is a perturbation around it. So you see, it's already system size, like length big.
Yeah.
Here, the smallest perturbation that I can do is similar. I have to kind of take one extra line and wrap it around the other direction. Or maybe I can kind of remove one of these lines, right? I mean, there's some. But so you see that in terms of those arrows, these two situations are completely similar. So in terms of arrows, the ground state here is like hugely polarized in this direction, and the ground state here is hugely polarized in this direction. So it's kind of just, in terms of the arrows, these two pictures are related by just a rotation, and you can check it.
Yes.
If you rotate the vertices, it's just, so that's why it's, and it's kind of like, so here you see that the corrections are already degree K or L in, let's say K is equal to L, and it's already the degree, the length of the system are the smallest perturbations around here, which is very different from what I was doing here, where I have very kind of small and local perturbations around it. So it already shows a little bit that here, you know, these phases, they're going to be completely different phases of the 6-vertex model. This one is kind of, it will be gapped. There will be a big kind of gap a cost for making excitations. Whereas in this case, you can make, I kind of, it's obvious that the local move that you do is you kind of flip this little path going down there, right? So you have just tiny little variations around it, and it modifies the 4 vertices, which is like degree 4 correction, and clearly there are n many because I can do it around any of the faces. So this is one of the local moves. Now I computed this part for you. So you see that this is local and it's kind of much softer. So this will be some sort of critical phase, which is capital. Any other question?
Questions from the online audience? Okay, they disappeared.
Okay.
So thank you.